Today we're going to take a look at key features of rational functions. Now there are about 6 key features. Those key features include discontinuity, both non-removable and removable. If you have a non-removable discontinuity, we call it an asymptote, and if you have a removable discontinuity, we call it a hole in your function. So a rational function can simply be written as f of x is equal to px over qx. If we look at this as two separate polynomials, that's all that creates a rational is you have one polynomial divided by a second polynomial. Independently, they have their own purpose. So we use the numerator, the polynomial in the numerator, when we're looking for x-intercepts, and we use the polynomial in the denominator when we are looking for points of discontinuity or where the function's undefined. So the domain of any rational function is all real numbers with the exception of those points of discontinuity, the places where our graph is considered undefined or where our denominator is equal to 0. So there are 3 examples of rational functions. In the first example, we can see that the denominator, if I was to try to set that equal to 0, I would have x squared plus 1 is equal to 0. And if I solved for x, I would realize, okay, I have an imaginary solution here, which means that there's no real number that my denominator will ever have to be in order to equal 0. So here we have 0 points of discontinuity, or our domain is considered all real numbers because every single value on the x-axis does have a y value or an output. If we look at the second rational function here, we have this new hole. It's considered a hole in our graph, and holes in graphs are points of discontinuity, but we call them removable because if we look at the factored form of our polynomial, we do have 2 factors, one in the numerator and one in the denominator, that technically can cancel out. So this is what we call a hole in our graph or removable discontinuity, whereas in the third rational, we do not have any kind of factor that would cancel out. And if I set my denominator equal to 0, I have a point of discontinuity at x is equal to 2. Since it's non-removable, it does create this asymptote at x equals 2. We call it a vertical asymptote. And we're also going to be able to look at some horizontal asymptotes that also occur when we're looking at rational functions. So a little bit of information on points of discontinuity. When the denominator is equal to 0, we say that the domain is undefined, or that there is a point in the domain or in my x that cannot be included as part of the domain or even a solution to the function. So when graphed, we say that we call them points of discontinuity, or that the graph is undefined. So in the example x plus 1 divided by x plus 2, if I was to set the denominator equal to 0, I would have a point of discontinuity when x is equal to negative 2. So we say that all real numbers can be included with the exception of x is equal to negative 2. The graph x plus 3 times x plus 2 divided by x plus 2 has what we call a removable discontinuity. So unlike the example previously, if we look at that first function here, there are no factors that can be canceled, whereas in my second example, I have the factors x plus 2 that can be canceled. Now, that's still considered a point of discontinuity because I do set my denominator equal to 0. And so I do have a point of discontinuity at x cannot equal negative 2, or a point of discontinuity, at x is equal to negative 2. However, those 2 factors do cancel out. So we call it a removable discontinuity. And what removable discontinuities do is just simply to create a hole in the graph, whereas non-removables create asymptotes. our removables simply create a hole in the graph. So if I was to simplify this down, this could simplify down to y is equal to x plus 3. When you're looking at the holes in your graph, what you want to be able to do is tell me exactly what value for y your hole is at. So it's redefining this domain, saying, okay, nothing works, everything works except -2. But at -2, technically it cancels out. It creates this hole. So in order to get the y value, we would evaluate our simplified polynomial at that point of discontinuity. So I get my hole, my point, is located at -2 and 1, because if I evaluate my simplified polynomial at that point of discontinuity, I get a y value or an output of 1. So my hole, the hole in my graph, is at -2, 1. So let's do a couple examples here. So I've got the polynomial x plus 3 divided by x squared minus 4x plus 3. One of the first things that I want to do is put this in factored form so that I can see if I have removable or non-removable points of discontinuity. And this factors in, the denominator will factor into x minus 3 and x minus 1. So I do know I have discontinuity because I have a denominator, and I have a discontinuity at x cannot equal positive 3 and x cannot equal a positive 1, because those two values, when inputted into the denominator, are going to give me a value of 0, and you can never have a 0 in the denominator. So that affects my domain. So I can say my domain is equal to all real numbers, with the exception that x cannot equal 3 and x cannot equal 1. And they are non-removable, so they're also going to create vertical asymptotes later on. So if I need to look for my x-intercept, what I'm going to do is set my numerator equal to 0. So I'm looking for when y value is 0, what is my x? And so we know that anytime your numerator is set to 0, your entire fraction is equal to 0. And so if I solve, I get x is equal to -3. So I have an x-intercept at the point -3, 0. And my y-intercept is where the entire function is set equal to 0. So my output value is 0. So I want to see what is my input value. So I take my function, and my function was y is equal to x plus 3 divided by x minus 3 times x minus 1. And I simply put in a 0 where all of the x's are, because my y-intercept occurs when my x value is equal to 0. So I'm going to plug it in, 0 plus 3 divided by 0 minus 3 and 0 minus 1. This gives me a positive 3 on the top with a -3 times the -1 on the denominator. So 3 over 3, and so I have a y-intercept of 1, because 3 divided by 3 is 1. Let's take a look at another one. This one will have a hole in it, just kind of giving you a heads up. This is what would happen if we have a removable point of discontinuity. So I'm going to start by first factoring the numerator and the denominator. So I have x minus 4 and x plus 1 divided by x minus 4. And I start off always knowing that my discontinuity occurs when my denominator is equal to 0. So I know that I cannot have a value for 4 in my domain. So my domain is going to say all the x values, all real numbers, except that x cannot equal 4. Now, if we look at our factors, I have an x minus 4 in both the numerator and in the denominator. So that is going to create a removable discontinuity or a hole in my graph. So I'm looking at my function, and I do have two factors that cancel out. And so my simplified function is x plus 1. And what we're going to do is evaluate that at the only point that we cannot use, which is x is equal to 4, to see where exactly does the hole in my graph occur. So if I substitute in my 4, I get a y value of 5. So I can say, okay, I have a hole at the point 4, 5. And if we look at the graph in the lower left-hand corner, we can see, okay, well, I had two polynomials. One was a quadratic divided by a linear, and I had two factors that canceled out, and so my graph looks like the linear function x plus 1 because that's what my polynomial simplified down to. However, at that point of discontinuity, we have a hole. We don't have an asymptote. An asymptote would cause the entire function to curve away from the, or curve as it approached the asymptote. But this is just simply a hole in the graph that occurs at the point 4, 5. If I needed to find the x-intercept, I could use my simplified polynomial here. And if I set my y value equal to 0, I would be looking at x plus 1 is equal to 0. And so I have an x-intercept at -1. So that ordered pair would be -1, 0. And my y-intercept is when x is equal to 0. For my y-intercept, I would simply evaluate the function when f is equal to 0, so I can still use that modified polynomial, that simplified polynomial, and I get a y value of 1. So I also have a y-intercept at the ordered pair 0, 1. Now, when you have the removables, or those factors that cancel out, they create the hole. But in the first example, we did not have any removables. We only had non-removable points of discontinuity. So those non-removable point of discontinuities create something known as an asymptote. So we have two types of asymptotes. We have vertical asymptote, which does occur when your denominator is undefined. So those non-removables are called asymptotes. They also have horizontal asymptotes that occur based off of the degree of the polynomial. So horizontal asymptotes compare the degree of the numerator to the degree in the denominator. So what the degree is just the largest exponent. So for example, the square or the cube or the 4, the 5, the 6. You're looking at where is your largest exponent in your polynomial from your numerator and in the polynomial from your denominator, and that relationship determines your horizontal asymptote. So for example, if you have a degree in your numerator that's larger than the degree in your denominator, let's say you have an x cubed in your numerator and an x squared in your denominator, 3 is greater than 2, you will automatically have a horizontal asymptote at the line y equals 0, so right at the x-axis. If your numerator is less than your denominator, so the degree in your numerator is smaller than the degree in your denominator, so for example, you have an x squared up top, but you have an x cubed in the bottom, 2 is smaller than 3, you don't have a horizontal asymptote. There is none. But when you have the degree of your numerator equal to the degree in your denominator, let's say you have an x squared in your numerator and you have an x squared in your denominator, your horizontal asymptote occurs at the line that compares the coefficient of that leading degree to the coefficient of the other. So an example would be, let's take a look at this first one here. 2x divided by x minus 3. If I'm looking for the highest degree, I'm going to go to the x with the greatest exponent. Now these ones have an exponent of 1. So their degrees are exactly the same. So what I would do is compare their coefficients. So the coefficient of the leading degree in the numerator is the 2, and the coefficient of the leading degree in the denominator is a 1. So 2 divided by 1 gives me a horizontal asymptote where y is equal to 2. In my second example, I have my numerator has a leading coefficient, or has a highest degree of 1, and my denominator has a highest degree of 2. So my numerator is less than my denominator, and the rule says that if your numerator is less than your denominator, then you do not have a horizontal asymptote. You may still have vertical asymptotes that occur at those points of discontinuity, but you do not have a horizontal asymptote. My third example shows when your numerator is greater than that of your denominator. So in the numerator of my third example, y squared divided by 2x minus 5, my highest degree in my numerator is a 2, whereas the degree in the denominator is a 1. Anytime that your numerator is larger than your denominator, you will automatically have a horizontal asymptote at the line y is equal to 0, or right on the x-axis. So using those degrees to help come up with your horizontal asymptote, the relationship in those degrees comes up with your horizontal asymptote. So what we're going to do is take a look at an example that encompasses all of these key features. So I've got the function x squared plus x minus 12 divided by x squared minus 4. So the first thing that I'm going to do is put this in factored form so that I can look at some points of discontinuity, or my x-intercepts or my y-intercepts a lot easier. So my numerator factors into x plus 4 times x minus 3, and my denominator factors into x plus 2 times x minus 2. So I know, because I'm working with a fraction, that my discontinuity is going to occur when my denominator is equal to 0. So I know that I do not have a domain that includes the number 2, or I'm sorry, negative 2, or the number positive 2, because x plus 2 equals 0 gives me an x value of negative 2, and x minus 2 equals 0 gives me an x value of positive 2. So I have these points of discontinuity. One of the first things I want to ask myself is, are they removable or are they non-removable? And if they're removable, then I know I need to go in and find the holes in my graph. But if they're non-removable, then I know they become asymptotes. Now, just a reminder, the only time that they can be removed is if the factors can be canceled. And in this example, the factors cannot be canceled, therefore they are non-removable. So my domain of my function is all real numbers where x cannot equal negative 2 or x cannot equal 2. Now, as far as holes are concerned, we said both of these are non-removable, so we do not actually have any holes in our graph. Instead, we have a vertical asymptote. Our vertical asymptotes occur at x is equal to negative 2 and x is equal to 2, because those are the 2 points, or the 2 inputs that create those points of discontinuity. So we know that they're asymptotes because they are non-removable. Since we're working with asymptotes, we might as well take care of our horizontal asymptotes. So our horizontal asymptotes compares the degree of the numerator to the degree in the denominator. So if I look at my numerator, I have a degree of x squared, or a degree of 2. And in my denominator, I also have a degree of 2, which means that I need to compare their coefficients. So the number directly in front of those. So I have, my numerator has a coefficient of 1. My denominator also has a coefficient of 1. So I have a horizontal asymptote at y is equal to 1. And I have 2 vertical asymptotes at y is equal to negative, or x is equal to -2, and x is equal to +2. I do want to find my x-intercepts, which means I need to set my numerator equal to 0. So I'm going to use my factored form, set it equal to 0, so I have an x-intercept when x is equal to -4 and when x is equal to +3. So written as an ordered pair, I would have -4, 0, and I would also have 3, 0. When I'm looking for my y-intercept, I'm simply going to evaluate my function when all my x values are equal to 0. So I plug in a 0 for all my x's. And I get a +4, a -3, divided by a +2 times a -2, which gives me -12 divided by -4. So I have a y-intercept when x is 0, y is 3. So that is how you take all of the key features and put them together. You're looking at domain, you're looking at whether you have your points of discontinuity as asymptotes or whether they are holes, so whether they're able to be canceled or not be canceled. You have your horizontal asymptotes, which is the relationship in the numerator and in the denominator as far as the degree of polynomial. You have your x-intercepts where your y value is equal to 0 and your y-intercepts where your x value is equal to 0. You can always use Desmos as a means for graphing and checking your work. Desmos will plot your x and y intercepts. You can visually see your vertical and horizontal asymptotes, and I believe that it plots your points of discontinuity when they are removable, so your holes in your graph. It's a nice way to just double check your work, but that's about it. So taking a look at kind of all these things that we've already studied and have culminated together into these rational polynomials.